Hey guys, what's up? So in this video, we're going to be talking about the mathematical theory of transmission line impedance. We're going to be going over the full derivation of getting our input impedance at some length. So let us just begin. So we can start off with the schematic of the equation. We're going to have some series resistance and some series inductance along the length of a transmission line. We're going to have some shunt capacitance and shunt conductance along the length of this transmission line. Now we just cut this transmission line into a small segment of length dx. Now before this structure, we're going to have v plus dv. We're going to have I plus di. Now after our waves travel through this section of transmission line, we're going to have shaved off dv. So we're going to just end up with v. We're going to shave off a little di. So we're just going to be left with I. Now our series impedance is given by R plus j omega L, and our shunt admittance is given by G plus j omega C, where G is your conductance, C is your capacitance, L is your inductance, and R is your resistance. Now, after some circuit analysis and Ohm's law, we could come up with a voltage equation, V is equal to I times Z. So we're going to have V plus dV minus V is equal to IZ times dx, because we're just looking at this small subsection. And same thing with our current. I is equal to V over Z. Well, in this case, we have shunt admittance, so we get V times Y dx. So now we could cancel our V and minus V, and we're going to be left with dV is equal to IZ times dx, and solving for dV by dx, we get I times Z. We could take our second derivative, and we need to remember that Z is constant throughout this structure, and only our current will be changing with respect to X. So that's where our derivative gets distributed to just di by dx. We could substitute in our impedance equation R plus j omega L. We could do the same thing for our currents. I and minus I cancel out, and we could solve for di by dx is equal to V times Y. Take our second derivative, and remembering that our admittance stays constant, so we're just going to have dV by dx. So we're going to end up with these two equations right here. Let's take a look at our voltage equations first. We have the second derivative times this bracket times di by dx. Well, we already know what di by dx is. It's just v times y. And we know what y is. It's just g plus j omega c. So in red, we have that expression right there. And analogous for our current, we have I times z. We have our current in purple, and we have the z, r plus j omega l right there. Now you can notice that both of these equations have those two same brackets. Now that's known as something called the propagation constant, gamma. Well, we define gamma squared is equal to those brackets because if you're taking a course on differential equations, this will make a lot more sense to you. But once we solve these differential equations, we're going to end up with an input wave and a reflected wave. The input wave is traveling one way and the reflected wave is traveling the opposite way. That's why E is to the power of positive or negative, one being forward and one being backward. Same thing with our currents. Electricity reflects. Now moving forward, we have these equations right here. Now let's take a look at when x is equal to 0, right at the start of our transmission line. We haven't traveled any length on our transmission line. We're looking at the starting point when x equals 0. Now e to the power of anything 0 is just 1, so our voltage would just be Vn plus Vref. And same thing with our current. We get I at 0 is In plus I reflected. And we know that I is equal to V over Z. So we could write our current equation in terms of voltages reflected and input voltages. So let's do that. I in, well, that's pretty easy. V in over Z naught. I haven't really talked about Z naught, which is the characteristic impedance. Maybe I should have actually made a slide. Oh, I'm sorry about that. And I ref is negative V ref over Z naught. Now, why are we getting a negative? It's because when our current hits the end of a transmission line, it's going to reflect in the opposite direction. You get negative current. So now here are our final equations, all in terms of voltage in and voltage reflected. Same with our current. Now moving forward, we just derived these two equations right here. So let's find our input impedance. Z at 0, input impedance. When x is equal to 0, well, that's just our voltage at 0.0 and our current at 0.0. So let's substitute in those two purple equations, and we get this fraction right here. Well, notice that Z naught is on both of these terms, so we could combine this fraction. Now Z naught will come to the top, and we could move Z naught to the other side. So we end up with Z in over Z naught is equal to this reflected voltage, input voltage buoy with a positive and negative. Now moving forward, we have Vn minus Vref in orange. Let's move that to the other side. Let's distribute Zn and Z naught to this fraction. And let's combine our like terms. So I've color-coded them so you could see where all these terms are really moving. Finally, well, not finally, let's factor out Vn and let's factor out Vref. That's in purple and red. We're going to end up with a yellow boy and a green boy. Well, let's create this fraction right here, Vref over Vn. This is something called a reflection coefficient. It's telling you the ratio of reflected and input voltages. And notice that -1, we could really express that as Z naught over Z naught. And +1, you could reflect that as Z naught over Z naught. And let's combine these fractions together now. So we have the same Z naughts on the bottom. So they'll combine into both terms and they'll end up canceling out. And finally, we'll be left with this equation right here. This is our input reflection coefficient. Now, this is a really important equation. If input reflection coefficient is 0, well, how can this equation be 0? Is if Zn is equal to Z naught. That means we have a perfect match. There is no reflection, full transmission. If we get a -1, if gamma is -1, that means when the voltage comes in, it's fully reflecting back with a phase change of 180 degrees. Now, if gamma is +1, it's reflecting back, but not with a complete phase change of 180 degrees. So let's move forward. So we have our gamma in, which we just derived. What about our gamma at a load? Well, we're just going to replace Z in with ZL, so the load impedance. And now we can look at something, we could look at our impedance at some length. Before we're looking at our input, now let's take a look. What if our load was like 50 meters away, 5 millimeters away, 50,000 kilometers away? Now we could substitute something called L. Well, we know L is the length, and let's just go through it. And for the time being, let's get rid of our reflected voltage and write it in terms of gamma, because gamma tells you how much reflection is coming back. Right? Vref over Vin is equal to gamma. So let's bring our Vin to the other side. We could express Vref in terms of just Vin and gamma. So let's substitute that in. So everywhere where we had reflected, those were always the second terms. We just replaced it with gamma L times Vin. Now let's factor out Vn and let's factor out Vn over Z for our voltage and current. And we're going to be finding our impedance, so VL over IL. And let's substitute those two equations. So I took this equation right here in our numerator and this equation right here in our denominator. We notice Vn and Vn cancel out and Z naught comes to the top. So that's why we have this equation right here. Now what we could do is we substituted in our gamma as our ZL guy, and I highlighted in blue because we need to find the greatest common denominator. So let's do that right there in blue. So we have a factor of ZL plus Z naught over ZL plus Z naught on our e to the minus gamma L. Now we could combine our fractions and the fractions will cancel out. And what do I mean by fractions? ZL plus Z naught is the same as ZL plus Z naught on both terms. So you could combine that into one fraction. Same thing with the bottom, and they'll cancel out with each other. So now we just end up with this. Now let's distribute our e to the powers. So we get these guys right here. Now let's combine all our ZLs and Z naughts together. So we're going to end up with this, and I color coded it so you can see what's really going on. And then let's factor out our ZL and Z naughts. So now we're left with e to the gammas, like negative versions. Now we need to remember our hyperbolic cosine identities. And let's move the 2 to the other side, and we're going to be left with e to the positive guy minus e to the negative guy. We have e to the positive guy plus e to the negative guy. And let's substitute that into our equation and just remember hyperbolic tangent. So look here, e to the negative guy plus e to the positive guy, well, that's just 2 times hyperbolic cosine. E to the negative guy minus e to the positive guy, well, that's just hyperbolic sine. So let's substitute those in. Well, let's factor out all the 2's, and the 2's will cancel out. And at this point, we have a pretty nice equation. We could leave it in this form, but in most textbooks, you'll see it written in terms of hyperbolic tangent. So let's factor out a cosine, hyperbolic cosine, and they will cancel out with each other. And we're going to end up with this final equation right here. Now, this is the full derivation of the input impedance at some length of a transmission line using Z naught, ZL, and the length of your line and gamma. We'll talk more about gamma later. Thanks for watching.